Hi, I'm Will Stephenson, and I'm presenting our work on local optima and cross-validation. Cross-validation is widely used for tuning hyperparameters, but isn't always well understood. We show that even in the simple case of cross-validation for tuning ridge regression, the cross-validation loss can have multiple local optima. We give some ways to identify when this won't happen, but we also show that the presence of local optima is in general a complex issue. This work was done with Zachary, Frangella, Madeleine, Udell, and Tamara, Broderick. So why are we talking about simple models like ridge regression? It's because that despite the fact that large, complicated models are becoming popular, simple models still enjoy really wide use. I think this is because they're easy to use, they're interpretable, and they tend to have really strong theory backing up their performance in practice. Like, for example, we're talking about ridge regression, which is just one of the most widely used statistical models in general. Now, we often tune the hyperparameters of such models by minimizing the cross-validation loss. Now, there is existing theory about this practice that says the globally optimal hyperparameters have good properties. Now, how are we going to get at these global optimal hyperparameters? Well, typically in practice, people use either grid search or gradient descent to optimize the CV loss. However, I want to stress that these optimization methods may fail in the presence of local optima. Right? Grid search, for example, can always verify that you found a local optimum, but it could be that the global optimum lies in between your grid points, or maybe more likely outside the range of your grid. So we study local optima in the cross-validation loss. And in particular, we focus on leave one out cross-validation for ridge regression and show that one, the loose CV loss may unfortunately, for the purposes of optimization, have local optima. Two, that the presence of these local optima has a complicated dependence on the inputs to the regression problem. And in particular, we show that they're not some weird edge case, that these local optima actually exist in real regression problems. And then three, we show some conditions under which the loose CV loss has no local optima. Now, let me just, we're really going more deeply into things. Let me get down some notation and background on CV and ridge regression. So in ridge regression, our data is going to look like some covariates xn, which are d-dimensional vectors, and then some responses yn, which are real valued. And then we have regularization parameter, which is going to be some scalar lambda that's positive. What we're doing in ridge regression is we're positing a linear model between these covariates and responses, and how we're going to estimate the parameters of that linear model is via theta hat of lambda, which is going to be defined as the argmin over all theta, sum of capital N terms, where the nth term is the squared loss on predicting the nth data point, plus lambda times the squared norm of theta. Right? This is just standard ridge regression, which is to say standard L2 regularized least squares. Okay, so to use this estimator in practice, we have to pick a particular value of lambda. And the way that this is really commonly done in practice is to select lambda by minimizing the leave one out cross-validation loss, or loose CV loss, which looks like this. That is, we select lambda star as the argmin of L of lambda, where L of lambda is the loose CV loss, which is just exactly the sum of, again, capital N terms, where the nth term is the squared error loss of predicting yn using theta hat slash n. What theta hat slash n is exactly equal to theta hat, except we've omitted the nth data point from the training loss. Right? That's why it's leave one out cross-validation. Now, existing theory says that the globally optimal theta hat of lambda star has good properties. In particular, it says something like tuning, selecting lambda star by minimizing the cross-validation loss is just as good as if you had selected lambda by minimizing the true out of sample error. So it's sort of as good as you could possibly get. However, this theory assumes that we can efficiently find lambda star. And in particular, a really common difficulty for optimization is the presence of local optima. So we might want to know whether or not there are local optima in the loose CV loss valve. Okay, well, one reason why we might feel positive about this, that there might not be any local optima in L, is because the typical kind of cartoon illustration of L has no local minima in it. Typically in introductory lectures or in textbooks or whatever, you'll find pictures like this, where the low-CV loss is this nice smooth function. It starts out kind of moderate, comes down, has this well-defined minimum, goes back up, and tapers off. Right, this is really easy to optimize. And so maybe when we're first trying to think of, okay, well, how can we generalize this past this cartoon picture? We might think optimization, no local optima, convexity. Right, that's a typical way of guaranteeing there are no local optima. However, it's pretty easy to see that this picture is not a convex function. And in fact, it's a pretty straightforward proof that we show L is almost never a convex function. Okay, however, this cartoon is a quasi-convex function. What quasi-convexity means is that the level sets of the function are convex sets. The important thing you need to know for this talk is that quasi-convexity guarantees that there are no local optima. At least there are no sort of non-trivial local optima. So we might want to ask, well, okay, in this case, is L always a quasi-convex function? Unfortunately, we show that the answer to this question is no. So here's an example in the bottom right. It's on a real data set about predicting the quality of wines. And you can see there are, in fact, local optima on this function. So we might, instead of trying to guarantee that L is always quasi-convex, try and understand instead when L is quasi-convex. So to do this, it's helpful to get a little bit more notation down first. So I'm going to let capital Y be the n-dimensional vector of responses, let capital X be the n by d matrix of covariates. And we're going to say that X has a singular value decomposition equal to USV, where U is the matrix of left singular vectors. It's an orthonormal matrix. S is a diagonal matrix with positive entries on the diagonal, where these diagonal entries are the singular values or the spectrum of X. V is an orthonormal matrix, which is the right matrix of right singular vectors. Okay, so there's a lot of degrees of freedom here, lots of different things that are going into the regression problem. There's Y, there's U, there's S, there's V. We actually show that the quasi-convexity of L doesn't depend on some of these things. So first of all, we show it doesn't depend on the norm of Y. So we can take Y to be a vector on the unit sphere. Doesn't depend on the matrix of right singular vectors V. So we can just take this to be the identity matrix. And finally, it doesn't depend on the scaling of the singular values S. So we can scale them however we want. It doesn't change the quasi-convexity. Now, it turns out that once you kind of remove these degrees of freedom from the problem, and then also consider a special case of n equals 3 data points and d equals 2 dimensions, it turns out that you can then reduce Y and U to be sitting on the unit circle. In particular, what this means is we can parameterize each of them by scalars between 0 and 2 pi. And so then if we fix the singular values S, we can grid up all possible regression problems and numerically check if they're quasi-convex or not. So what we've done, and what we're going to do is we're going to discretize these unit circles, each into 200 evenly spaced points. And I'm showing you here a 200 by 200 pixel image, 1 pixel per regression problem. So we fix the singular values S. So you can see at the top, it's listed S1, the larger singular value is 2.4, the lower one is about 0.007. And what we've done is we've colored a pixel yellow here if the resulting regression problem has a loose CV loss that is non-quasi-convex. And we've colored a pixel purple if the loose CV loss of the resulting regression problem is quasi-convex, meaning it sort of has no local optima. My takeaway here is that, wow, there's some really weird patterns here. That the presence of quasi-convexity has this like really regular but somehow very mysterious pattern at the same time. And I wanted to say right now that we don't fully understand these patterns. So if somebody wants to work on this and try to like characterize exactly what these shapes are and what's going on in this picture, that would be awesome. But we can't currently tell you what's going on. However, what we can note is that this picture was made for fixed singular values. So let's see what happens when we change the singular values a bit. In particular, what I've done here is I've increased the lower singular value by about an order of magnitude. And we can see that there's more purple in this picture, and there's more quasi-convexity. And so what we might say is that, hey, we made the spectrum more uniform. The singular values got closer to each other. And then we got more quasi-convexity. Okay, that's interesting. Let's see if this pattern continues. And so we make the lower singular value bigger again, and indeed, there's even more purple here. And so we see that we got an even more uniform spectrum, we got even more quasi-convexity. So while individually these pictures are pretty complicated looking, they suggest a pretty clear conjecture, which is that more problems have a quasi-convex Lucey loss when the spectrum becomes more uniform. Okay, so we might want to ask, hey, can we actually prove when this happens? Unfortunately, in general, this conjecture is not true. We show in our paper that you actually can have non-quasi-convexity even when you have a perfectly uniform spectrum. So basically that is to say we're going to need some assumptions for this to be true. Just broadly, the form these assumptions take is that the matrix of left singular vectors U is sufficiently uniform. And then also we're going to need that the unregularized estimate theta hat, that is when lambda equals 0, is sufficiently regular. It fits the data well and behaves well, essentially. So given these assumptions, we state our main theorem, which is that if the spectrum S of the covariate matrix is sufficiently close to uniform, the number of data points n is sufficiently large, and the above assumptions hold, then the Lucey loss L is guaranteed to be quasi-convex. Okay, so that's a very theoretical statement. We might have some questions about how what this theorem implies for practice. In particular, one of our big questions was that, hey, we proved that if the spectrum is sufficiently close to uniform, then we get good stuff. Well, how close to uniform is sufficiently close? Does it need to be like absurdly close to uniform, or just like, kind of close? So to investigate this, the way we decided to investigate this is to take a bunch of different settings of singular values. And then for each setting of the singular values, generate a bunch of random linear regression problems. And then for each setting of the singular values, we can compute the fraction of the Lucey losses that are non-quasi-convex. So that's what I'm showing you over here on the right. So the y-axis is measuring the fraction of non-quasi-convex problems, and the x-axis is measuring the distance of the spectrum from uniformity. What we've done is we've pre-processed things so that the largest singular value is equal to 1. So that's why the distance between the spectrum and the vector of all ones is kind of a reasonable way of measuring distance from uniformity. And so we can see when we're over here on the right side of this plot, when we're very non-uniform in the spectrum, that there's a lot of non-quasi-convexity, right? Like 60% of the problems are non-quasi-convex. However, it doesn't take too long, that is, we don't have to go too far to the left, get too uniform, in order to hit 0 on the y-axis. That is to sort of have guaranteed quasi-convexity. Second, you might want to note that our theorem said, hey, n, the number of data points, has to be sufficiently large. And you might be concerned that, hey, maybe this theorem is just like ultra asymptotic and only really kicks in once you have so much data that you actually don't need regularization in the first place. So you don't need to minimize the cross-validation loss. And I'll say that's actually not true. So this picture was generated with n equals 20 data points in d equals 5 dimensions. So very non-asymptotic regime. Finally, we made some bunch of assumptions for a theorem. You might ask, well, how necessary are those assumptions? And I'll just say that we have some experiments in our paper that suggest these assumptions are necessary. Okay, so let me just recap. We said, hey, bridge regression is this really widely used model. It's very old too, so it seems like it must be the super well understood model. However, we showed some surprising behavior in its Lucey loss. That is, there can be non-quasi-convexity or local optima in the Lucey loss. We showed that the presence of this non-quasi-convexity is a complex function of problem inputs, and we made some sort of mysterious squiggly plots like this. And then we proved that when the spectrum is sufficiently close to uniform, you're guaranteed to have quasi-convexity. So here are paper details down below. And if you're interested in learning more, check out a link to the actual paper in the YouTube description. And thanks a lot for listening.